Hey, in this tutorial we're looking at section 7.2, which is on a review of differentiation techniques. So for some people this should just be a review, for other people there might be a few things in here that we haven't seen a lot of. But look, the skills that we've got in this section is really our bread and butter of our differentiation. Okay, so we'll go through a whole heap of things that I've got here at the start, okay, of different functions and how we differentiate them. And then we're going to be looking at the chain rule, product rule, and quotient rule. So to start off with, if we have some function x to the power n, okay, then the derivative is n x to the power of n minus 1. So what we do is we take our power, bring it out the front, and then reduce our power by 1. Remembering if n is a negative number, okay, well, it's going to become more negative as well. So in this case, we say n does not equal 1. Okay, but if it does, it doesn't matter too much. It just means that that term's going to drop out in terms of our x. It's not going to be there at all. And if n is equal to 0, okay, so it's just a constant, then that constant's going to disappear when we take our derivative. Okay, if we have a constant out the front of our function this time, so a x to the power n, okay, simply it becomes a n x to the power n minus 1. So the only thing that happens is we have that constant out the front in both of them. Okay, if we have sine of x, our derivative is cos of x. If we have sine of kx, then the derivative is k cos of kx. If we have sine of gx, then it's g dash of x cos of g of x. Now, as we'll get to shortly, this is really an example of the chain rule, which we're going to see in a minute. Okay, similarly, if we have cos of x, then the derivative is negative sine of x. If we have cos of kx, then the derivative is negative k sine of x, kx. If we have cos of g of x, then it's negative g dash of x cos of g of x. Okay, so again, this one's just an example of the chain rule. Okay, also, if we've got tan of x, okay, then the derivative is 1 on cos squared of x, which equals sec squared of x. So we're going to say the derivative of tan is sec squared of x. So that means the derivative of tan of kx is k sec squared of kx. Okay, and similarly, if we have tan of g of x, then it's g dash of sec squared of g of x. Again, application of the chain rule. Okay, when we have a look at our logs, so log to the base e of x, the derivative is 1 on x. Log to the base e of kx is 1 on x again. So this time our k actually disappears. Again, that's from our chain rule, an application of our chain rule there. Okay? If we have log to the base e of ax plus b, then it's simply a on ax plus b. Okay? And you can see here from, in this example, if we did have a b, okay, then we'd say that we'd had k on kx, the k's would cancel out. That's why we have just 1 on x. If we have log to the base e of g of x, then the derivative is simply g dash of x on g of x. So it actually works out quite well for a lot of our questions. And again, that's a chain rule. If we have e to the power of x, then our derivative is simply e to the x. Okay, really nice easy one there, it doesn't change. Okay, if we have e to the kx, then it becomes k e to the kx. If we have e to the gx, then it's g dash x e to the g of x. Okay, so this is a real snapshot of all our functions that we're looking at, what the function is, what the derivative is. Now, just to make sure that we're comfortable with some of our terminology, we have some function f of x, then the derivative is denoted as f dash of x. We can take the derivative of a derivative, okay, and we get f double dash of x. Okay, and we could keep going, you can do triple dashes, or if we took the derivative of f double dash, we can say, we can start putting numbers there. Okay, so we know it's the third derivative. Okay, the other way we can do it is we can say, sorry, if we have some function y, then the derivative, and we say, I don't know, y, actually, we say we've got something like y, and it's going to be in terms of x. So you could say, I don't know, x squared. Okay, we're going to ignore this side, but we're just saying that we've got function of y in terms of x. I just don't want to quite write it like this. It's because we say that the derivative can be written as dy dx. Okay, and we read that as the derivative of y with respect to x. Okay, and it's a little bit different when we start talking our second derivatives. This way can work quite well with the chain rule, as you'll see coming up. Okay. So we'll get stuck into some worked examples. Okay, so there's two kind of ways that we can do our derivatives using the chain rule. Okay, this way that I'm going to show you to start off with is different to the way they're used in the textbook, but it matches in them with the same way that we use it for the product rule and quotient rule. That's why I wanted to show you this way first, and then I'll show you a way similar to in the textbook. So for this one, okay, we're looking at worked example 1, okay, and we're just simply saying if f of x equals square root of 4x squared plus 9, we want to find the derivative, okay, f dash, okay, at 1. So what we're going to do is find our derivative, then sub 1 in. Okay. Now for our chain rule, okay, this is examples where we have a function within a function. Okay, so you can see that we'd have a square root function, and then we've got this function inside of it. Okay, so our example is that we've got g of h of x. Well, the square root would be g of x, and 4x squared plus 9 would be h of x. So the good way to set this up is go, okay, actually write down what g of x would be. And sometimes you've got to think a little bit about what this function would be, because it's not quite as obvious. So we're saying that's our square root function, so square root of x. Right? And that would mean that h of x is equal to 4x squared plus 9. Okay, so what we need to do, okay, to find our derivative, okay, up here is we need h of x and we need g dash of x. Okay, so we're going to take the derivative of these parts by themselves. Okay, so g of x, or g dash of x, okay, to work out that, first thing we need to do, okay, is rewrite our g of x and say it's g of x equals x to the power of a half. Okay, square root is the same as the power of a half. Then we can simply say that we've got g dash of x is equal to a half x to the negative a half. Okay. From before, we've got our power, bring it down the front, okay, and then reduce the power by 1. So we say g dash of x then is equal to 1 over 2 root x. Okay, when we have a look at h dash of x, okay, a little bit more straightforward, bring our power down, make it 8x to the power of 1, we don't worry about that power, and constants just disappear, so our 9's gone. Now what we can do is we can use this rule here, okay, and basically piece together what we need. So if we have f of x equals g of h of x, then our derivative is f dash of x equals h of x times g dash of h of x. So we need our g dash first, okay, it's going to be our 8x, okay, and then we need our g dash of x, okay, which is here. Okay, so then we're going to times it by our 1 over 2 square root, but now wherever we'd have an x in here, we've got to put our h of x. This is our 4x squared plus 9. Okay, we can simplify a little bit and say that f dash of x is equal to 8x over 2 square root of 4x squared plus 9, which equals 4x over the square root of 4x squared plus 9. Okay, and we're there. Okay, we do need to, however, sub in 1. That was the last part. Can't forget about that. So we need to go, well, f dash of 1 equals 4 times 1 over square root of 4 times 1 squared plus 9. That's going to be 4 over square root of, well, 1 squared is 1 times 4 is 4 plus 19 is 13. Okay. Then what we can do, because we always like to actually do our rational denominators. Okay, so we can times that by root 13 on root 13. Okay, which is going to make us 4 root 13 on 13. Okay, which is all we need. Okay, and we're done. So we can have a look at this second one here. Okay, so I'll do this one a little bit more along the lines of our textbook. Okay, so for this one, okay, we need to identify, first of all, a bit of a substitution that we can do. So what we're going to do is we're actually change this to our terminology of y and say that it's y equals 2 cos to the power 4 of 3x. Okay, and think of this as y equals 2 outside of cos of 3x to the 4. Okay, now we can see a little bit easier that we've got a function within a function. So what we're going to do is we're going to say let u equal cos of 3x. Okay, so now we've got a function that is y equals 2u to the power of 4. Okay, so putting that u back in here. Okay, what we now need to do, okay, is we're going to use the chain rule in terms of dy dx, which is that dy dx equals dy du times du dx, because our du's could simply cancel out to give us our dy dx. Okay, so in order to do that, we need a derivative of y with respect to u. So we can say dy du equals 8u to the 3. So bringing our 4 down, reducing our power. Okay, we can also say our du dx. Okay, for that one. So when we take the derivative of this, derivative of cos is negative sine. We've got to bring our 3 out. So it's negative 3 sine of 3x. Now if you're being pedantic, you'd actually need to do the chain rule on this as well. But that's a little bit silly and a little bit long-winded, so we don't worry. Okay, so simply we can construct our equation now. Say, well, dy dx equals our dy du, which is 8u cubed, okay, times minus 3 sine of 3x. Okay, and at this stage we'll bring our minus 3 and our 8 together, and we need to sub our u back in. So you say dy dx equals minus 24 cos cubed of 3x sine 3x. Okay, and we're finished. Okay, so there's two different ways of doing it. This way will match our product rule and quotient rule way. This way matches our textbook way, and there is definite advantages to this way as well as advantages to this way. It all depends on context. Later on in this chapter you're going to be looking at related rates problems, and this way is by far the best way to think about it. Okay, other times this one can be a bit better. So I'll keep going with some worked examples. Okay, so this time we're doing f of x equals 4 sine of 2 on x, and we need to find f dash of 6 on pi. Okay, so what we're going to do is we'll do it in terms of this way, and we'll say y equals 4 sine of 2 on x. Okay, so we're going to this time let u equal 2 on x. So then we have an equation y equals 4 sine of u. Okay, so we need, again, remember we've got dy dx equals dy du times du dx. Okay, so we'll take our dy du first. Dy du is going to equal, derivative of sine is cos, so we end up with 4 cos of u. We say our du dx. Okay, well for our u, we need to think of that as 2, we need to think of u as 2x to the negative 1. Okay, so we get minus 2, so because our negative 1 comes down, x to the negative 2, because we'll reduce our power by 1. Okay, now we can bring it together and sub in what we want. So we've got our dy du is our 4 cos of u, 4 cos of u times our minus 2x to the negative 2. So now we've got to sub our u back in, and we're going to rearrange this a little bit as well and say that dy dx is equal to minus 8 cos of 2 on x over x squared. Okay, it's just going to look a little bit nicer when we do that. Okay, and what we can do now is sub in our value that we wanted. Okay, so again, and the other way, the reason why this doesn't work that well is you can't really say, we can't write it like this when we're in this form, so we can't do our f dash bit. So, but we could easily say that f dash of x equals our minus 8 cos of 2 on x over x squared. Okay, so what we'll do is we'll get our f dash of pi on 6 going to equal minus 8 cos of 2 on pi on 6 over our pi on 6 squared, okay, which will equal, when we simplify that a little bit, because it does look pretty messy when we do that, and sorry, this should be 6, oh sorry, I've gone the wrong way, this should be 6 on pi, and that should be 6 on pi, sorry, went the wrong way there. Okay, so when we do simplify that, okay, it's not a horribly nice thing that happens here. Oh, this part's not too bad because you can flip and multiply and say that we've got 2 pi on 6, okay, or pi on 3. Okay, over here we can, it still gets a little bit messy, but in the end what we get to, and this is just in the textbook if you want to have a bit more of a look, okay, and again this should be our 6 on pi in there, is that we get minus pi squared on 9. So I just skipped a few steps there in the textbook there, just purely because we're running out of a little bit of room. Okay, this time we'll have a look at this one. Okay, we just want to find the derivative. Okay, so this time we're going to set it up our other way. Okay, and we're going to say, well, g of x is going to equal e to the x. Okay, and h of x equals cos of 4x, so g dash of x equals e to the x, and h dash of x is equal to our minus 4 sine of 4x. Okay, so now we can build it up here because we're h dash, so that comes out the front for our, we start working on our f dash. Okay, it's our h dash, which is minus 4 sine of 4x, okay, times by our g dash, okay, of h of x. So wherever we've got an x, we've got to put in our h of x again. So we go e to the cos of 4x. So this is going to look similar to what we had, okay, simply because of the properties of e to the x, the derivative just being e to the x. Okay, so we're pretty much done there. We can just make it a little bit nicer. Minus 4 sine of 4x e to the cos of 4x. Then see, it was a little bit more space saving doing it this way compared to doing it this way. Okay, it just depends on how much work you got to do when you've got to find these derivatives. Okay, we'll keep moving on. Okay, we need to look at the product rule. Okay, so as the name suggests, the product rule is used for when we've got two functions multiplied together. So if we have f of x each equals g of x times h of x, then the derivative is g dash of x h of x plus g of x h dash of x. Now you can't stuff this one up too much, as long as you remember it's the derivative of one of them times the original of the other plus the original of the first times the derivative of the second. It doesn't matter if you mix up these orders and go g of h dash of x plus g dash of h of x. Doesn't matter if you muck up that order. Okay, so we don't use really our dy dx notation too much for this, okay, because the easiest thing is really to do it like we were and just say, well, what's g of x? In this one, we've got f of x equals x to the 4 sine of 2x. Well, g of x is our first bit, so I'm going to say x to the 4. Our h of x, well, that's going to equal our sine of 2x. Okay, well, now we can find our g dash of x. Okay, well, that's going to equal 4x to the 3. Okay, and h dash of x, okay, is going to equal minus 2 cos of 2x. Okay, now just be mindful that if these ones get harder, what can happen is we've got to do a fair bit of work to actually find these derivatives. Okay, we have to apply the chain rule, etc., to actually find these. Okay, so what we do now is we just build up our equation. Okay, so we say then that f dash of x, okay, is equal to derivative of one of them, which is 4x cubed, times the original of the other, sine of 2x, plus, we've got the derivative of the second times the original here, but I'm just going to do it the other order so it makes it look a little nicer. So we'll actually say that minus 2x to the 4 cos of 2x. Okay, because we've got our minus 2 here, it will actually end up being a subtraction. Okay, and if you like, you can take out some common factors and such to make it f dash of x, okay, equals 2x cubed outside of 2 sine of 2x minus 2x cos of 2x. Okay, if you want to make it look a little nicer, you can do that. Okay, so we'll keep moving along. So this time we've got x to the 5 times e to the minus 2x. So again, g of x is going to equal our x to the 5. Our h of x this time is going to equal e to the minus 2x. Okay, for this one. Okay, so when we do this, then we're going to go g dash of x, which is going to be 5x to the 4. And our h dash of x for this one is our constant comes down the front, so it's minus 2e to the minus 2x. Okay, and again we can build it up and say that we've got f dash of x equals 5x to the 4e to the minus 2x. Okay, and again we've ended up with a subtraction, so we say minus 2x to the 5e to the minus 2x. Okay, and to be honest, I'll probably leave it at that. It's not too bad the way we've got it. Okay, if you like, you could bring out some common factors, and it means we're going to end up with f dash of x equals x to the 4e to the minus 2x outside of 5 minus 2x, if you like. Yeah, it's not that great, so it's up to you if you really want to worry about that step. Okay, moving on to the quotient rule. Okay, now quotient rule is for when we have f of x equals g x on h of x. Okay, now this rule is important that we get the order right. So it's f dash of x equals h of x, so the one that's on the bottom, times the derivative of what's on the top. Take what's on the top over the derivative of what's on the bottom. Now this is important because g of x times h dash of x minus h of x g dash of x is not the same as this. If you muck up the order, you're going to be in trouble. Okay, and it's all over h of x squared, so your bottom function gets squared. Okay, so we'll have a look at this worked example that we've got. Okay, so let's set it up again. G of x, okay, is our 3 sine of 2x. Okay, h of x equals our 2x to the 4. Okay, so g dash of x, it's going to be, sine goes to cos. Okay, so it's going to be 6 cos of 2x, and h dash of x is going to equal 8x cubed. Okay, so now we can build up our solution. So we can say we've got our f dash of x equals our h of x, so 2x to the 4, times our g dash of x, which is 6 cos of 2x, minus g of x, which is our 3 sine of 2x, times our 8x cubed, all over our h of x, 2x to the 4 squared. Okay, so we need to simplify this a bit and neaten it up. Okay, so what we can do is we can bring out some terms here. So I'm going to be able to bring out, when you do this, well, we've got our 2 times our 6 is 12, and our 3 times our 8 is 24. So we're going to be able to bring out 12x to the 3, right, outside of, so our numbers are gone there, we've still got an x though, so x cos of 2x, okay, take 2 sine of 2x. Okay, so far so good. Okay, over our 4x to the 8 when we square that. Now again, we can cancel out some terms here and say we've got f dash of x. Okay, well, 4 cancels out, so we're going to have 3. Okay, we can cancel out 3, x cubed with our x to the 8. So we've got 3 outside of x cos of 2x. Take 2 sine of 2x over x to the 5. Okay, and we're finished. Okay, if you like, and they do it just like this, where they write 3 on x to the 5 times x cos of 2x. Take 2 sine of 2x. You can write like that if you prefer how that looks. It's up to you. Okay, next one. But if f of x equals 3x on square root of 4x squared plus 9, find f dash of x. Okay, so for this one, again, g of x equals 3x, h of x equals square root of 4x squared plus 9. Okay, g dash of x equals 3. H of x though, got a bit of a problem here. Hey, because we've got a chain rule problem here. So what I like to do is just go, okay, I'm going to go my h dash of x. Okay, I'm going to put it there eventually, but I'm going to leave that spot at the moment. Okay, and what can be handy is changing colours. Well, it's handy for this at least. So I'm going to change colours. I'm going to look at finding what h dash of x is down here. Okay, so we've got h dash of x. So put our h of x equals our square root of 4x squared plus 9. Okay, so with this, okay, in the past we were doing it where we actually had our g of x and h of x, but now this is h of x. So you could pick other letters, or what I'm going to do is I'm going to go back to the other way of doing the chain rule, okay, and say let u equal 4x squared plus 9. We could replace our h of x with y and say we've got y equals square root of u. Okay, so dy du then, well remember, we can think of this as u to the half. So it's a half u to the minus a half. Okay, and we've got to do du dx then, derivative of this part, which is 8x. Okay, so our dy dx is our half times 8. Well, we know that's going to be 4. So we're going to be 4x, okay, over, because we're u to the power of negative half, the square root of u, which was all this part. So 4x squared plus 9. Okay, and remember that is equal to our h dash of x. Okay, so now that we've got that, okay, we can put it back up in here and say, well, we've got 4x on the square root of 4x squared plus 9 for our h dash of x. Okay, so there's a fair bit going on there. Okay, so now we can build up our equation though. Okay, and say that we've got our h of x, which is the square root of, so saying f dash of x now, okay, it's the square root of 4x squared plus 9, okay, times g dash of x times our 3 minus g of x, which is our 3x, times h dash of x, which is our 4x on square root of 4x squared plus 9, and that's all over our h of x squared, our square root of 4x squared plus 9 squared. Okay, so we've got a little bit of work to do here. Okay, so we've got f dash of x, okay, is equal to, well, we've got 3 times the square root of 4x squared plus 9, okay, minus, sorry, done that a bit long, minus 12x squared over our square root of 4x squared plus 9 over, we can just say a square root and our squareds are going to cancel out, so 4x squared plus 9. Okay. Alright, now they do a little bit of work in the book, just a bit of rearranging, and look, I'm clearly running out of space here, so we'd had to do a little bit of work to our top line, okay, make our denominators the same, okay, so we can bring them together, and then we can do a bit of flip and multiply, because they're going to be a fraction over a fraction, and say then that f dash of x, when you actually finish doing all that rearranging, okay, believe it or not, okay, we actually get 27 over the square root of 4x squared plus 9 cubed. Okay, and now I know it might seem a bit of a leap between this step and this step, okay, but doing that little bit of algebra, then you can get there. And again, I apologise, I've run out of room, but the few steps are in there that you can do. Now, you'll also notice if you've been following along with those two sections with the product rule and quotient rule, so they do actually show you how you can do it in terms of dy dx, okay? And I'll just write the little rule here, the equivalent of it, which is that y equals u over v. Okay, and then that means that our dy dx equals our v times du dx minus u times dv dx all over our v squared. Okay, so you can use this method if you like, and I'll just flick back a page. So probably, in all fairness, should do it for this one as well, which is y equals u dot times v. So we've got y equals our du dx times v, okay, plus our u times dv on dx. Okay, so you can look at it like that if you like. I just much prefer the setting out of the way we've done it here with our g of x, our h of x, our g dash of x, our h dash of x, sub in what you need, and I just find it's a lot easier to follow along. Okay, so we've got two last worked examples to do. This is all we have left in this section. Okay, so if there are just a couple of different ones. Okay, it's largely just using our different rules for tan and for logs. Okay, so for this one, you can see it's actually a product rule question. Okay, because we've got function times a function, so we're going to say, well, g of x is equal to x squared. Okay, h of x is equal to tan of 2x on 3. Okay, so far so good. With g dash of x is equal to 2x. Now h dash of x. Okay, remember for this one, our tan of x. Okay, when we take our derivative of that, okay, is, well, we've got to bring out what we have here. Okay, our 2 on 3 has got to come out the front. Okay, so it's 2 on 3 sec squared of 2x on 3. Okay, so we look at what's the derivative of this essentially and bring it out the front. Okay, of sec squared. Okay, now we've got everything we need, we can build it up. So again, remember it's a product rule, so we can't actually stuff this up. We just got to remember derivative of one times the original of the other plus the other way around. So we can say our g dash of x times our h of x. So our 2x tan of 2x on 3, okay, plus, okay, this one times this one. So we can say we've got 2x squared on 3 sec squared of 2x on 3. Okay, and I say not really great to do much here. You could take out the 2x, but really it's not going to make things look that much nicer. Okay, so we're finished up with that one. Okay, then, oh no, sorry, we want to find it when it was at pi on 2, so we can do that. So we can say, well, f dash of pi on 2. And you'll see, even though you go, oh yeah, it's got tan and we're one of our nice values, it doesn't actually work out that great because of our other x's out the front. So really we go 2 outside of our pi on 2 times tan of 2 on 3 times our pi on 2 plus 2 times our pi on 2 squared on 3 sec squared of 2 times our pi on 2 on 3. Okay, so it doesn't look that great. Okay, when we start working through that, okay, then we get, okay, just looking at this f dash of pi on 2. Okay, let me just have a quick look to see what we get for some of these. Okay, so as I said, it's really not very nice. Okay, so when we do this, okay, then obviously the way you need to think about this is 1 on cos squared. Okay, and when we do that, I'll just give you the next step. Now they've written it in the different order, so let me just get this right. So we've got, I write it as 10 of our pi on 3, because our 2's are going to cancel out here and leave us with pi on 3. Okay, times by, well, we've got 2 times pi on 2, so it's going to be pi. Okay, plus, okay, for the next bit, we've got to have our 2 on 3 times pi squared on 4, okay, times by 1 over cos squared of pi on 3. So yeah, it does the same thing. I wrote differently, but it'll do the same thing there. Okay, so we get f dash of pi on 2. Okay, well, tan of pi on 3 is root 3. So we're going to get root 3 pi. Okay, plus we're going to get, from this part here, we're going to get pi squared on, well, when we do this, we're going to, we can cancel our 2 with our 4 to leave us with a 2. So we're going to get 6 here times, okay, well, cos of pi on 3 is a half, and that's got to be squared as well. Okay, so we're getting there, f dash of pi on 2 equals root 3 pi plus pi squared on, well, it's 6 on 4. Okay, so we're getting there, and when we simplify everything, I'm running out of room, so I'll just do the last line. Okay, we end up, when you simplify everything, pull everything out that you can, what we get is pi outside of 2 pi plus 3 root 3 on 3. Okay, looks a little bit complicated, but we get there. Okay, and the last one we've got one more example. Hopefully we've got enough room to squeeze them in. Okay, this is going to be a chain rule question. Okay, so what we'll do is we'll do our g of x is going to be our log to the base e of x. Okay, our h of x is going to be 3x plus 5 over 3x minus 5. Okay, so g dash of x, okay, is 1 over x. That's our nice bit. Okay, our not quite so nice bit, of course, is the next part. Okay, but actually I just realised I've made this harder for ourselves than what it needed to be. Much harder. So sorry, scratch that. Okay, that was silly, because what we would have had to do is do this and do the quotient rule, and oh, we'll end up looking horrible. Much easier. What we can do, okay, is use our log laws. Okay, we know that f of x, okay, is equal to log to the base e of 3x plus 5 minus log to the base e of 3x minus 5. Okay, so we need to make sure we look for things like that. Okay, that would have been, yeah, a bit of a muck up if we'd gone the other way. And look, at the end of the day, we would have got right. It just would have been quite horrible to actually do. Okay, because this works so much better. Because when we do this, okay, when we take the derivative of this, okay, then what we get, okay, is we always get the derivative of what's inside our brackets. Okay, or this is our example where we had log to the base e of a x plus b. Well, it was our a term. Okay, or 3 over 3x plus 5. Okay, because it goes over what you had. Minus, again, 3 over 3x minus 5. Okay, if you like, you can do a bit of work here so we can add our fractions together. They do it in the textbook. So we do a cross multiplication. So we get 3 outside of 3x minus 5 minus 3 outside of 3x plus 5 all over our 3x plus 5 times 3x minus 5. Okay. So we're doing that just so we can simplify it down the best we can. Okay, so when we do that, what we can do is we can expand out our top lines and our bottom line for that matter, f dash of x. Okay, well we've got 3 times 3x will give us 9x minus 15 minus 9x, and we're going to be take 15. Okay, so when we do that, oh sorry, can't forget our bottom line. 3x by 3x gives us our 9x squared. Okay, our 3x by our minus 5 is going to cancel out with our 5 by our 3x. So we can say we just got take 25. Okay, so we get f dash of x equals, well, 9x and our 9x will cancel out. Our minus 15 and our minus 15 will become minus 30. Okay, over our 9x squared minus 25. Okay, that's actually the end of this section. Now I know we've done lots of worked examples. There's probably a lot to get your head around. I know compared to the methods course, it's going to seem pretty heavy because in the methods we actually have a separate section for the chain rule, product rule and quotient rule, where in specialists we actually have it all up together. Hey, that's okay. Just make sure you get some good notes down for these examples and how to use the different rules. And just make sure, again, you're wary of the quotient rule. It's the one that will trip you up with having these in the wrong order. So make sure you get your head around that one really well.